Welcome to the Deep Dive, the only show that takes massive stacks of data and turns them into immediate, actionable knowledge for you, the well-informed learner.
Today, we are not just talking about security. We are talking about eliminating the single greatest, most dangerous, and oldest vulnerability in computing history.
The hard-coded password.
A hard-coded
is
password.
for us.
We are building a digital fortress.
And the problem we're tackling here is just, it's absolutely massive. We're talking about developers accidentally committing secrets, API keys left in config files, database connection strings just lingering in source control.
And often exposed to the entire internet.
I mean, the numbers we pulled for this deep dive are truly staggering. One source we found points out that over 23 million high-value secrets were reportedly leaked into public code repositories in 2024 alone.
23 million. That is not just a statistical risk. That is a systemic failure point across the entire industry. And those leaks are happening because the underlying model, relying on a secret that someone somewhere has to store or remember, it's just fundamentally broken.
Exactly. So our goal for this deep dive is to really understand the modern solution. We want to show you, our listener, how modern cloud applications, specifically in Azure, achieve what is known as secretless authentication.
Right.
We're shifting the entire security model so that identity, a robust, verifiable machine identity, is the new perimeter, not the network.
And this is a deep dive into architecture. You'll gain a really clear understanding of the architectural blueprint, the crucial security trade-off you have to make, and we'll even get into some of the implementation tutorials on how you actually connect all this together.
Using services like Azure Key Vault and Managed Identities.
Exactly.
Okay, so let's unpack this. By the end of this conversation, you won't just know the terminology. You'll know exactly how to structure an application that inherently resists secret leakage and adheres to, the highest standards of cloud security.
To really appreciate the solution, I think we have to start by accepting that the old security paradigm is, for all intents and purposes, dead.
Right.
For decades, security was built around what we used to call the moat and castle model.
The idea being that once you got past the firewall, the moat, you were inside the castle, and everything inside was assumed to be relatively safe and trusted.
Yeah, and we spent a fortune on those barriers. Firewalls, intrusion detection systems, VPNs.
All of it.
And that model utterly collapsed because the modern enterprise is borderless. We have multi-cloud environments, services connecting from third-party SaaS vendors, a remote workforce.
People are accessing critical data from literally anywhere on the planet.
Exactly. The traditional network boundary has dissolved, rendering that legacy perimeter defense insufficient. In fact, I'd argue that relying on it just concentrates the risk. It makes the VPN gateway a single, highly lucrative target for attackers.
I remember when the solution to remote work was just spin up more VPN capacity. Now, the idea of treating anyone who authenticates via a VPN as trusted seems terrifyingly naive.
It is, because if an attacker compromises a laptop outside the castle walls, and that laptop connects via VPN, the attacker is suddenly inside with minimal checks.
Bruh.
In the cloud, this failure is amplified 1,000 times.
So every request, whether it comes from a human in a coffee shop or a serverless function in another region, has to be scrutinized.
Every single one.
So identity, both human and machine, has become the definitive perimeter. This is that strategic shift, right? Identity-centric security.
Correct. And that's the cornerstone of the Zero Trust security model. The directive is deceptively simple.
Never trust, always verify.
Never trust, always verify.
Yes.
It assumes there is no implicit trust granted to any identity or device, regardless of whether they're inside or outside that old network boundary.
We hear the term zero trust constantly. Let's break down the 3 core principles that really anchor this architecture because they guide every single choice we're about to discuss.
Okay. First, and this is the most crucial one, verify explicitly.
Which is much more than just asking for a password or an MFA code.
Oh, way more. Authentication and authorization have to be based on all the available data points. We're talking about risk signals.
Okay, so what are those extra signals? It's not just who I am, but what else?
We check identity, of course. But we also check location. Is the request coming from a geography we expect? Or has the user suddenly appeared in 2 continents simultaneously?
Right. A classic impossibility signal.
We check device health. Is the device running an updated OS? Is the disk encrypted? Does it have up-to-date antivirus? And we look at session risk. Is this connection part of some unusual behavior pattern?
So that context-aware access control means if my laptop is suddenly flagged as having an unpatched vulnerability, The system doesn't just block me. It might limit my access to just the bare minimum or even just remediation tools until my device is compliant again.
Exactly. The system verifies explicitly that the user, the device, and the connection context all meet the security requirements for the specific resource they're trying to reach.
Okay, so that's principle one. Principle two, use least privilege access, or POLP. This one feels foundational to security in general, but how does Zero Trust enforce it more strictly?
Well, in the old model, sometimes people got permissions based on their job title, which meant really broad access.
Hmm.
In Zero Trust, permissions must be strictly scoped to the minimum necessary to perform a single, specific task.
So if a web app only needs to read one config file from storage,
It gets read-only access to that one file, not contributor access to the entire storage account.
the goal then is limiting lateral movement. If an identity is compromised, the attacker only inherits this tiny slice of permissions, which makes it way harder for them to pivot across the network.
It dramatically reduces the blast radius, which leads us directly to the third principle, assume breach.
We have to architect our systems with the acknowledgement that failures and breaches are, well, inevitable.
That's a tough mindset shift, isn't it?
Mm.
It means you stop focusing all your effort on prevention, you start dedicating serious resources to containment and detection.
Right. If we assume breach, we design robust segmentation, we enforce least privilege everywhere, and we make sure we have extensive logging and monitoring enabled.
Precisely. The focus shifts from just keeping people out to minimizing the time an attacker can remain inside and the damage they can do.
And connecting this back to our topic application architecture, our source material highlights that this means abandoning the idea of handling identity ourselves.
Yes. This brings us to a crucial mandate in the cloud world. It's actually one of the core design principles for secure Azure applications.
Design principle number 8.
Exactly. Use an identity service, or IDEAs. The platform team must provide a robust cloud-native identity as a service platform, like Microsoft Entra ID.
Why is this non-negotiable? Why can't a sophisticated company just build their own identity provider?
Because operating your own identity system is incredibly complex, massively risky, and highly expensive to maintain. Security protocols change constantly. Think about the rapid adoption of FIDO keys, WebAuthn.
The constant evolution of MFA protocol.
If you build it yourself, you inherit the liability for every phishing attack, every password compromise, and every security update you miss.
It just sounds like a fast track to technical debt and legal exposure. The expertise needed to run a secure identity system at planetary scale is beyond the scope of 99% of organizations.
It is. And this brings us right back to the root problem we're solving today. Eradicating static credentials.
Right. Passwords, shared secrets, API keys.
They're the antithesis of the verify explicitly principle. They increase the risk of theft, phishing, brute force attacks. And even if they're perfectly secure in the code, they demand complex manual management.
Rotation every 60 days, secure storage, access control, all of which introduces human error and operational overhead.
So the strategic goal of this whole identity and access fortress then is to replace those brittle, static credentials with verifiable, dynamically managed machine identities.
Shifting the security focus entirely away from secret management and toward roles, scopes, and contexts.
Now we can drill down into the core mechanisms that make this secretless reality possible.
You're right.
Applications running in Azure need to connect to other resources. A web app needs to talk to a database. A function needs to access storage. A VM needs to retrieve a secret from a key vault. How do they do this without a secret?
This is where Managed Identities, or MI, arrive as the undisputed gold standard for Azure-native workloads.
A managed identity is an automatically managed identity principle in Microsoft Entra ID. It's provided to Azure Compute Resources. Think of it as a specialized type of service principle.
But with one critical game-changing difference.
Azure handles the entire credential lifecycle.
This is the essence of that secretless promise. Since Microsoft handles the generation, the rotation, the secure storage of the underlying credentials, developers never see them.
Never touch them.
And therefore, can't accidentally leak them. It's a true zero-trust, zero-secret model for internal components.
And the mechanism's really elegant. The application doesn't store a password. Instead, when it needs to talk to a resource, it makes a request to a local, secure endpoint on the Azure host environment.
A non-readable IP address only accessible from within that resource.
Right. The Azure Fabric intercepts that request, verifies the resource is authorized to ask for a token, retrieves a short-lived OAuth 2.0 token from Entra ID on the resource's behalf, and then hands it back.
So the application receives a valid security token without ever having touched a username or a password. The identity is just baked into the runtime environment itself.
Exactly. And importantly, to prevent attackers from trying to trick the application into requesting a token, the application has to include a specific security header. It's a highly protected, closed-loop system.
Okay, so once we decide to use managed identities, we have to navigate the choice between the two types, system assigned and user assigned. Let's dig into the lifecycle nuances here because this choice has huge governance implications.
The System-Assigned Managed Identity, or SAI, is the default, and it's the simplest choice. It has a lifecycle that is tied directly to a single Azure resource,
A one-to-one relationship.
a one-to-one. If you enable MI on an Azure function, the SAI is created in Entra ID. When you delete that function, the identity is automatically deleted too.
That automatic cleanup is a massive security benefit. You eliminate the risk of orphaned credentials just lingering in the environment, holding stale permissions that an attacker might find later.
It provides the highest degree of isolation.
Heh.
However, for environments that operate at scale or need shared access, we often need the User-Assigned Managed Identity, or UIMI,
A UMMI is created as a standalone top-level resource in Azure.
meaning it has an independent lifecycle from the compute resources it's assigned to.
I see where the governance complexity comes in, but why is that independence necessary? Why would you want that?
Because it allows a UAMI to be assigned to multiple resources, a one-to-many relationship. Imagine you have a scale set of 100 virtual machines or 50 function apps, all performing the same background task that needs access to the same centralized log storage account.
Okay, so instead of configuring 100 individual security policies, one for each SAI, and having to manage all those permissions separately,
You define the permission set once on the UAMI, and then you assign that single UAMI to all 100 resources. If the security policy for the storage account changes, you update one UAMI policy.
and all 100 resources instantly inherit the new access rules.
It transforms that administrative nightmare into a manageable, centralized operation.
That's the key, manageability and scale. But the trade-off is clear. If those 100 VMs are deleted, that UAMI just remains until an administrator explicitly deletes it. You now have a governance responsibility to clean those up.
Precisely. If you're not disciplined about auditing and cleaning up unused UAMIs, you reintroduce that risk of orphaned credentials, which sort of defeats some of the purpose of adopting MI in the first place.
Now let's talk about service principals, or SPs. Our sources categorize them as essential, but carrying a higher inherent risk. If managed identities are so superior, why are service principals still absolutely necessary?
Managed identities are brilliant, but they are intrinsically linked to resources running within the Azure platform. The Azure Fabric is what manages the identity acquisition.
A service principal, though, is more of a generic application identity.
Right. It's a representation of an application in Entra ID, used to grant limited access to Azure resources from the outside world.
So if I have a workload that runs outside the Azure Compute Fabric, I'm forced to use a service principal.
Correct. The most critical use cases are things like, one, external workloads running on-premises, or in other clouds like AWS or Google Cloud. Number two is CI/CD pipelines, things like GitHub Actions or Jenkins. Those pipeline runners are ephemeral, often external to Azure, and they need explicit credentials to deploy resources.
And since SPs are used for external authentication, they reintroduce the exact problem MI was designed to solve: manual credential management.
Absolutely. The catch is that you have to generate the authentication secret, a password or a certificate store securely, rotate it regularly, and make sure it's never exposed in logs or source code.
If that SP secret leaks, any external actor can assume that application's identity and compromise your services.
It forces you to re-engage in that complex management game we were trying to escape.
It sounds like we should view the service principal as the controlled guest pass for an external contractor, whereas the managed identity is the secure employee badge for internal staff.
That's a perfect analogy. The choice isn't about which is better, but which is appropriate for the context. Managed identities offer a dramatically lower risk profile because they eliminate secret leakage.
Okay.
But they're restricted to the Azure internal ecosystem.
Whereas service principals are necessary for universal accessibility, external, hybrid, multi-cloud, but they carry a higher risk profile because they require that careful manual management and robust governance.
So the architectural recommendation has to be adopt a strict managed identity first policy.
Unambiguously. You only fall back to a service principal when the workload must run outside Azure, or the service doesn't support MIAuth yet.
And if you do use an SP, the governance must be immediate and robust. The SP secret must be stored securely,
Not in a YAML file.
not in a YAML file or an environment variable, but in an Azure Key Vault, which brings us to the next defensive layer of the fortress.
We've established that identity is the perimeter. Now let's talk about the impenetrable vault, where the secrets that must still exist are securely stored.
Right. So if managed identities are the ultimate way to achieve secretless access, then Azure Key Vault is the final defensive layer. It's the centralized, high-security repository for credentials that must exist.
Things like legacy database passwords, third-party API keys, TLS certificates.
All of that.
Yeah.
And its core value proposition is not just storage, it's control. By moving these high-value assets out of disparate config files and into Key Vault, we centralize distribution, we gain complete auditability, and we dramatically reduce the chance of accidental leakage.
And its security is stratified. Key Vault offers 2 tiers.
It does. The standard tier provides encryption using software-based FIPS 140 Level 1 validated libraries. This is solid, but if you have high security needs or specific compliance mandates, you have to look at Premium.
Premium is where the hardware comes in.
Correct. The Premium tier offers Hardware Security Module, or HSM, protection. These are dedicated physical devices. Our sources specify their FIPS 140-3 Level 3 validated Marvell Liquid Security HSMs.
Okay, for our listeners, what does FIPS 143 Level 3 validated HSM protection actually mean in practice? What do you get for that?
It means that the cryptographic keys are generated and protected within a dedicated hardware boundary. The critical promise is that the keys never leave the HSM.
Okay.
They're used for encryption and decryption operations inside the hardware, making them physically and logically inaccessible to everyone, including Microsoft administrators. It's government-grade security hardware.
That physical isolation is the key. Now, moving on, Key Vault security depends heavily on controlling who can access what. And this is where the architecture uses a crucial concept: dual plane access control.
Yes. We have 2 distinct security boundaries or planes. First is the management plane or control plane.
This controls administrative operations on the Key Vault resource itself.
Right. Think of actions like deleting the entire vault, updating its network settings, or viewing its properties. For this plane, only Azure RBAC, role-based access control, is supported.
And the second plane is the data plane.
The data plane is where you interact with the sensitive objects inside the vault, the secrets, keys, and certificates. This means adding a new key, retrieving a secret's value, or performing a cryptographic operation.
The segregation here ensures separation of duties. So an infrastructure admin with management plane access can delete the Key Vault, but they have no automatic rights to read the secrets inside.
Absolutely vital. And this leads us to the major architecture evolution that the sources advocate for so strongly, transitioning from the legacy access policy model to using Azure RBAC for the data plane.
Wait, I remember dealing with those legacy access policies. They felt clunky, but what was the major security vulnerability that prompted this entire shift toward mandatory RBAC?
Well, the legacy access policy model, which is native to Key Vault, it only operates on the data plane. And the primary security flaw stemmed from how it interacted with the Azure Resource Manager, or ARM.
So tell us where the loophole was.
The legacy model lacked granularity. Permissions generally applied to the whole vault, so if you could read one secret, you could often read them all. But the bigger problem was that the access policies were part of the resource definition.
Ah, I see. So since the access policies were part of the ARM resource,
A user who had the general-purpose contributor role on the Key Vault resource itself, a role often given to DevOps teams for managing infrastructure, could simply update the access policy list. They could effectively grant themselves, or any other user, full data plane access.
wow. So a general-purpose admin who is explicitly not meant to see sensitive application data could promote themselves to a data reader instantly. That's a massive security failure waiting to happen.
It fundamentally undermined the principle of separation of duties. And that is why Azure RBAC is the definitive recommended authorization system now. It's built on Azure Resource Manager, providing unified, centralized, and consistent access control across both planes.
What's the biggest governance advantage RBAC brings that solves that loophole?
Granularity and independence. RBAC roles are managed outside the Key Vault resource definition itself. But the most powerful feature is that you can scope access down to the individual object.
So you can create a rule that says, this specific managed identity is only allowed to get secret X and nothing else in this Key Vault.
That is true least privilege. The application can access one secret, not the whole vault, Even if the application is compromised, the attacker can't list or access the other 99 secrets in that same vault.
And it integrates with tools like privileged identity management or PM.
Precisely. PM allows you to define roles that must be actively requested and approved, and which expire automatically after a set time. It gives you that just-in-time access for truly sensitive administrative tasks, making that self-promotion loophole virtually impossible.
It's a significant layer of security control. And using RBAC means we can leverage built-in roles that align perfectly with that principle of least privilege.
Yeah, we should go through a few of those. For standard monitoring and auditing, you have the Key Vault Reader role.
This lets you read metadata, but not the sensitive content.
Exactly. Then, the most commonly assigned role to an application's managed identity is the Key Vault Secrets user. This role grants the ability to see the actual secret contents, but only through a GET operation. They can't modify or delete it.
That's the read-only retrieval permission most apps need. What about someone who needs full control over the secret's lifecycle?
That would be the Key Vault Administrator. They have all data plane permissions on all object types, but they still don't have permission to delete the vault resource itself. That's a management plane role, so it maintains that separation of duties.
Okay, so moving beyond access, we need protection against catastrophic mistakes or even malicious insiders. This is where the core data protection features become mandatory.
First up, soft delete. This is now enabled by default for all new key vaults, and once you enable it, you can never disable it.
Why is that permanent enabling so important?
It ensures that if a key vault or an object inside it is deleted, it remains recoverable in a soft deleted state for a configured period, typically 90 days. It buys you time. Without it, a rogue admin could delete the vault, and your keys are gone forever.
And the second layer is purge protection.
Purge protection is the ultimate defense. It prevents the permanent deletion, the purging of the vault, while it's in that soft deleted state. Once enabled, it also can't be disabled.
So if I have both enabled, an attacker would need not only the highly privileged purge permission, but they'd also have to wait out the entire 3-month retention period to permanently destroy the data. It forces a very deliberate, time-consuming process that you're much more likely to detect.
Exactly. It's a fundamental control against insider threats and certain ransomware scenarios.
And finally, we can't overstate the importance of logging. You have to log all user activity, all access operations, all security events. Without that complete, immutable audit trail, you can't meet compliance or perform forensic analysis when an incident occurs.
Logging is the necessary record of the Fortress's activity.
Okay, here's where it gets really interesting for me. We've architected this sophisticated fortress of identity and storage. We've defined the governance. We've selected the right hardware. But how does a developer actually hook into all this complexity without writing complex token retrieval code that just defeats the whole secretless purpose? We need an abstraction layer.
The implementation has to be low friction. If the secure route is harder than writing password equals secret, developers will choose the insecure path every time.
So Azure provides these high-level client libraries that abstract away the entire process.
Right. And let's start with the heart of the modern developer workflow, the component that enables this write once, deploy anywhere pattern. Default Azure Credential.
So Default Azure Credential is part of the Azure Identity Client libraries available in Python, .NET, Java, and so on.
It's a sophisticated piece of middleware whose primary purpose is to support a credential chain.
What does that credential chain actually do?
When an application asks for a resource connection, say, to a key vault, the default Azure Credential object automatically tries a predefined, ordered sequence of authentication methods until one of them succeeds.
This is the genius part. This means the same application code can run locally on my machine using my identity and then run flawlessly in production using the managed identity. I never change a line of code.
Exactly. When you're developing locally, the chain tries to use your identity automatically, your cache token from VS Code or the Azure CLI. When you deploy that app to an Azure App Service, the chain automatically detects the presence of the managed identity for that host and uses that to get tokens.
It eliminates that chicken and egg problem where you need a secret to retrieve a secret. The host environment's identity is the key that unlocks everything, and the developer's code stays identical across all environments.
It just significantly reduces hard coding risk because the developer never has to handle a production credential.
Now let's talk about managing application configuration versus managing high-value secrets, because they are distinct problems.
There has to be a clear separation of concerns. General app config IP addresses, feature flags, non-sensitive stuff, that should go in a service like Azure App Configuration.
But the high-value secrets database passwords, crypto keys, those must be managed by Key Vault.
They have fundamentally different security and auditing requirements.
So how do we combine them securely? How does an application get its database password without that password ever being stored in the app's config service?
This is solved using Key Vault references. These aren't the secrets themselves. They are secure pointers or placeholders that you embed in your application settings. It just looks like a secure URI at Microsoft.keyvault, secret name.
And how does that mechanism prevent plaintext leakage?
The magic happens at the application host level before your code even executes. When the Azure application host, like an app service, loads its settings, it sees that reference. It then uses the application's managed identity to authenticate to Key Vault, resolve the reference, and fetch the actual secret value.
And then it injects that value as a standard environment variable.
Right. So your application code just sees an environment variable named, say, dbPassword, containing the actual password. But that password has never been stored in a config file, a deployment artifact, or exposed anywhere in the portal.
That is the zero leakage configuration pattern.
This pattern also dramatically simplifies configuration refresh in large enterprises. Our sources highlight a concept called the Sentinel key.
Tell us more about the Sentinel key. I only saw a single sentence about this in the notes, and it sounds important for global deployments.
It's a phenomenal feature. The Sentinel key is just a specific, non-sensitive key stored in Azure app configuration that your application watches. When you need to push a configuration change, which might include an updated Key Vault reference across hundreds of app instances globally.
You don't want to restart them all at once.
Exactly. You want a coordinated, fast update. The Sentinel key acts as the tripwire. When you update its value, even just changing it from 1 to 2, the app configuration service notifies all the listening applications.
And those applications then automatically refresh all their configuration values at the same time.
Including securely refetching the latest version of any reference secrets from Key Vault, all without requiring a full application restart. It ensures rapid, coordinated global consistency.
That's resilience and security wrapped into one. Okay, let's tackle the last implementation piece. Containers, specifically Azure Kubernetes Service, or AKS. The traditional way of handling identity for containers was a major security hole.
It was. The older method, often called node identity, assigned managed identities to the Kubernetes node itself. This meant every single pod running on that node shared the same high-privilege identity.
So if an attacker compromised a low-privilege application in one pod, they instantly inherited the permissions of the entire host node, a complete violation of least privilege.
The solution is Workload Identity Federation, or WIF, which is enabled by Microsoft Entra Workload ID. This allows a pod to authenticate using its native Kubernetes service account, leveraging OpenID Connect or OIDC Federation.
Okay, let's slow down and define that architectural shift. What's the role of the service account here, and how does OIDC make it secretless?
The Kubernetes service account is the local identity within the cluster. With ByUF, the AKS cluster is configured to act as an OIDC identity provider. Then, Microsoft Entra ID is configured to trust the OIDC tokens issued by that specific AKS cluster.
So the pod doesn't hold an Azure secret. It presents its service account token, the OIDC token, to Entra ID, and Entra ID trusts that token because it knows the issuer is legitimate.
Precisely. The pod exchanges its short-lived service account OIDC token for a managed identity access token. This establishes a chain of trust federation without any secrets being stored in the pod config.
The identity and permissions are now granular, scoped per pod,
ensuring true least privilege access even within a dynamic containerized environment. This is the modern secretless way to manage container access.
That's a huge architectural jump forward, moving the security boundary from the node level all the way down to the individual workload level.
We've built an incredibly strong fortress, and we focused on eliminating secrets entirely. But we have to address the remaining secrets, right? Those necessary legacy database passwords, service principal secrets, the certificates stored in Key Vault.
And the fundamental rule of secrets management is that the security of a secret is inversely proportional to its age. The longer it lives, the greater the chance it's been compromised.
Which means automated regular rotation is non-negotiable. The industry standard recommendation is rotation every 60 days to minimize that window of vulnerability.
And trying to manually rotate hundreds of secrets every 2 months across a global enterprise it's impossible. Automation is critical.
This requires a highly reliable, event-driven pattern, Let's define that rotation architecture. It involves three core services.
The event source, the event router, and the rotation handler.
The event source is Azure Key Vault itself. You configure the secret to have an expiration date, and AKV publishes a specific event, the secret near expiry event, typically 30 days before that date. This is the trigger.
The event router is Azure Event Grid, which checks subscriptions and delivers that notification to the downstream logic.
And the rotation handler is the business logic component, usually an Azure function or a logic app. It receives the event, identifies the secret, regenerates the credential on the target service, and then updates Key Vault.
Our sources highlighted a crucial technical hurdle here for high-security environments. Many organizations use VNet-isolated key vaults with private endpoints.
Right. And if Key Vault is using a private endpoint, it's not accessible over the public internet. But Event Grid delivers events via a public IP endpoint, which the private endpoint blocks.
So the handler function never receives the notification.
That's the critical workaround. We introduce Azure Event Hubs as an intermediary trusted service. You configure Event Grid to deliver the event to the Event Hub endpoint, which resides inside the VNet.
And the Event Hub must have the Allow Trusted Microsoft Service to Bypass Firewall setting enabled,
So that the Event Grid delivery can succeed. We maintain high network isolation, but we enable the essential security automation by using Event Hubs as a trusted bridge. It's smart architecture.
Now, let's look at the actual logic inside the rotation handler for the two main scenarios. Scenario 1, single set credentials, like a traditional SQL database password.
The function app receives the trigger, identifies the secret, connects to the SQL server using its managed identity, generates a new random password, updates SQL Server with that new credential, and finally creates a new version of the secret in Key Vault.
The nuance here is crucial for application resilience. Since the update to SQL and the update to Key Vault are two separate steps, there's a tiny window, a few milliseconds maybe,
Where the consumer might retrieve the new secret from Key Vault, but the target service hasn't fully registered it yet.
So if the application immediately uses that newly retrieved secret, it will fail to authenticate until that brief lag closes.
Exactly. This means the consuming application must be built with robust, intelligent retry logic. It should handle a momentary auth failure by trying again, or maybe even checking its local cache to see if the old credential still works for one more attempt. Without that, automated rotation risks causing brief outages.
That's the kind of complex detail you definitely don't want to figure out at 3 a.m. during an unexpected outage. It highlights why this design pattern is so important.
Now, Scenario 2 is designed to achieve true zero downtime. Dual set credentials. We see this most often with Azure Storage Account keys.
Right. Azure Storage provides two keys, Key 1 and Key 2, which operate simultaneously. The rotation mechanism has to leverage this duality.
The rotation logic is safer because it operates on the key that is not currently being used by the application, or at least the one not currently stored as the latest version in Key Vault.
So the function first determines, okay, if Key 1 is in Key Vault, I need to regenerate Key 2.
Precisely. It calls the Storage Account API to regenerate the alternate key, Key 2. Once regenerated, it adds Key 2 as the new latest version in Key Vault. And the zero downtime is achieved because the applications, which might be cached on Key 1 for a short period, can continue operating normally.
Until their credential cache refreshes and they seamlessly switch over to Key 2, Key 1 remains active and valid during the entire process.
The transition is seamless. However, our sources included a significant warning associated with storage key rotation.
Yes, this is a critical dependency management issue.
Rotating an account-level storage key instantly revokes all associated account-level shared access signatures or SAS tokens.
That means if you have any application using a SAS token that was generated using the key you just rotated, that application immediately loses access.
Correct. The rotation logic can't just stop at updating Key Vault. It has to also immediately trigger downstream processes to regenerate any critical SAS tokens and update the consumers who rely on them. It's not a single step. It's a dependency chain that requires meticulous mapping before you automate.
So what does this all mean? We've covered everything from the paradigm shift to zero trust, the deep mechanics of managed identities, the governance revolution in Key Vault RBAC, and the complex automation for key rotation. If you're designing or securing a cloud-native app today, you have to implement a structured hierarchy for identity and access.
And that hierarchy should be crystal clear for every engineer and architect. First and foremost, managed identity first. If your workload is Azure-native, use MI. System assigned for isolation, user assigned for scale.
Second, if your workload is external or for CI/CD, you fall back to a service principal. But its credential must be securely stored only in Key Vault, preferably as a certificate.
Third, for all other necessary legacy secrets, you must use Key Vault and transition immediately to the Azure RBAC model to ensure fine-grained access, scoping permissions down to the individual secret level.
And finally, for everything that has a life cycle, automate rotation using Event Grid, event hubs, and functions.
The ultimate strategic goal here is maintaining that core design principle of least privilege. Every single component we discussed, managed identities tied to resources, Key Vault RBAC scoped narrowly, workload identity for containers, all work to ensure that even if a single resource is compromised, its access is so tightly scoped that the blast radius is minimal.
It reinforces that assume breach mindset with a resilient, identity-centric architecture, leading us toward a truly secretless enterprise that's ready for compliance and highly resilient to attack.
That brings us to our final provocative thought for you to chew on. Since managed identities are inherently tied to their Azure directory and subscription, they cannot be transferred when you move resources.
Oh, that's a big one.
If your organization acquires another company, or if you need to perform a data repatriation exercise that requires moving core application resources across subscriptions or directories, you have to delete and recreate those managed identities and reestablish all of their permissions from scratch.
What unforeseen complexity in terms of downtime, operational risk, and identity governance overhead does that introduce when you're trying to rapidly consolidate two enterprise environments? That governance hurdle surrounding identity lifecycle management is just as critical as the initial deployment.
Food for thought indeed.
Yeah.
And a powerful reminder that security architecture is never truly finished. It's always evolving to meet the demands of enterprise complexity.